In the previous video we looked at the idea that for a nucleus to become stable it needs to emit either matter or mass or energy. In this video we'll have a look at the different types of radiation. So we'll basically just sort of list them out and give some examples of what they are. The first one is alpha decay, and the symbol that we use for that obviously is the symbol alpha. Now an alpha particle consists of 2 protons and 2 neutrons. So in this case we're emitting mass from the nucleus in the form of 2 protons and 2 neutrons. 2 protons and 2 neutrons is otherwise known as a helium-4 nucleus. So we could represent that as 4,2He. Alternatively, it will sometimes be represented as 4,2 alpha to make it a bit clearer that it's an alpha particle. Now if we were going to represent that as an example, so the isotope uranium-238, so that has a uranium-238 has a symbol of U with 238 at the front and 92 being the atomic number. That would decay by alpha by emitting an alpha particle, so 4,2He, and the remaining stuff that's still in the nucleus would then become thorium-234. Now to make it a little bit clearer here, there's a few terms that we're going to use about these when we're looking at this type of decay. The one that we start with we're going to call it's known as the parent nucleus, and the one that we end up with is the daughter nucleus. So they're 2 terms that we'll just use to clarify whether we're talking about what we start with or what we end up with. One other thing to note here as well, just write that down as an example, but note that both the mass and atomic numbers balance. And the reason for that is to conserve both charge and mass. So in that, if you look across the top, we have values of 238 for the parent nucleus and then 4 and 234 for the alpha particle in the daughter nucleus, so the 238 is equal to 4 plus 234. Likewise down the bottom, 92 for the atomic number is equal to 2 plus 90. So we haven't lost or gained any protons or neutrons, they're all still there. They're just in slightly different arrangement so that the thorium has become more stable than the uranium. Note also here too that just because it's decayed it doesn't mean it's going to be stable. So the thorium-234 won't necessarily be stable, it may still be an unstable nucleus, and as a result it could undergo another form of decay itself. So that's the first type. The second type is beta negative, sometimes just referred to as beta, but I'm going to write beta negative to distinguish between beta negative and beta positive. Now the symbol that we use for beta negative is a beta with a negative beside it as well. Now this one's a little bit different. Beta negative is an electron from the nucleus, and you might sort of say, well hang on, electrons aren't in the nucleus. The reason why we end up with an electron in the nucleus is when a neutron is converted to a proton and an electron. And we also have another little particle here that we're not going to deal with now. We will deal with it in subtopic 7.3 when we get back to it. There's another particle here, it's known as an electron antineutrino. As I said though, we'll come back to that particular particle in a later subtopic. Now the equation that shows the neutron turning into a proton would be given by this one here. It's 1,1. So 1, 0 represents a neutron, 1, 1 represents a proton. So if you look at it, a neutron doesn't have any protons, so it's a 0 for the atomic number, but a 1 for the mass number because it contains 1 nucleon. A proton, on the other hand, has an atomic number of 1 and it's 1 nucleon as well. Now the symbol that we use for a beta particle is 0, negative 1 e. You might sometimes see it as 0, negative 1 beta, so it could be represented that way as well. And we also then have the neutrino. Now the symbol for a neutrino, sorry, it's not an arrow, it's just a line. The symbol for a neutrino, it looks like a V, but it's actually the Greek letter nu, N-U. So yeah, we'll just include it there. Note that it doesn't have any numbers in front of it. If you did want to write numbers, it'd be 0, 0, because it's not a nucleon and it's not a, obviously not a proton either. Now, I mentioned before that in that previous example that the thorium-234 itself might not be stable, and we can show here that it actually isn't, and it undergoes decay by beta negative. So the thorium emits an electron from the nucleus, and as a result we're left with 23491 Pa plus that electron antineutrino. Now you'll notice here that because the electron has an atomic number of -1, the atomic number of the daughter nucleus has actually increased. The number of protons and neutrons hasn't changed because we've had this neutron turn into a proton, so the mass number hasn't changed, but we do get a change in the atomic number as this electron is emitted from the nucleus. The next type is then positron decay. Sometimes also referred to as beta plus or beta positive, and in this particular type of decay we use the symbol beta plus instead. Similar to beta minus, except in this case it's a positron that's emitted. Now a positron is basically it's think of it as being an anti-electron. It's basically the same as an electron, the only difference is that it has the opposite charge. So it has the same mass, has all the other same properties, but it has positive charge instead of a negative charge. And we get a positron when a proton converts to a neutron. So a proton converts to a neutron, a positron, and another subatomic particle, the electron neutrino. And again, if we look at the equation that describes that process, that would be 11p goes to 10n plus 0 plus 1. Note that we put the plus there just to make it very clear that it's a positron. And the electron neutrino is now just the letter nu with a subscript e. So notice that the electron antineutrino has the bar across the top of it to indicate it's the antineutrino, whereas the electron neutrino doesn't have the bar across. But again, we'll get onto that in more detail in topic 7.3. An example of positron decay is carbon 11. So carbon 11 would emit a positron, and as a result we're left with boron 11. So again, the mass number doesn't change, but the atomic number does, plus that neutrino, the electron neutrino. And the final type of decay that we're going to look at is gamma ray emission. Now gamma ray emission, there's two aspects here to consider. The first is that when we have, I should mention the symbol here is gamma. A gamma ray is basically just a photon of energy, and it would be in the electromagnetic spectrum. It falls in the in gamma ray the region, and it's a photon of energy, and it's emitted. There's two situations where a photon of energy can be emitted. It can be emitted along with another type of radiation, so along with alpha or beta. And when I write beta here, I mean both beta plus and beta negative. So it can be emitted with either of those two decays, or when a daughter nucleus is in an excited state. Or an energized state. So a good example here is cobalt 60. So with cobalt 60, it will first of all undergo beta negative, so 0, -1. It then produces nickel 60, but that nickel 60 atom, nucleus, is in an excited state. And the way that we represent that it's in an excited state is simply to put an asterisk beside it. So keep in mind here as well, we'll still get the electron antineutrino will also then get a packet of energy, so we can add the gamma ray at the end there as well. Now the second stage of that decay is that the excited nickel nucleus will then decay to basically the same thing, so it's still nickel 60, but it also releases a gamma ray at the same time. So it looks like that sort of relationship is pretty straightforward. It's basically just a higher energy state, and then it settles down into a more stable state and emits some energy in that process. Now we could combine those two, and you could see that here that so those two stages ultimately combine. So if we start off with the cobalt, basically we're sort of just ignoring the fact that the nickel's in one of the daughter nuclei, and we could say that it's going to produce the electron, the beta particle, I should say, the nickel 60, the electron antineutrino, and it's also going to produce now two gamma rays. So we could write that in there as well. So that's kind of the combination of those two equations above, if we're only interested in the original nucleus and what it's produced. We'll have a look at a few of these in class, and I'll give you a few problems to do so you can get a good sense of how to balance these equations and make sure you know what's being produced in each of these types of decay.